This tutorial will describe how to use non-spiking chemical synapses in your projects. The standard method for two neurons to communicate is for the presynaptic neuron to fire an action potential. When the depolarization from the action potential reaches the synapse, it causes calcium to enter the cell, which leads to a release of a vesicle filled with neurotransmitter. This transmitter then activates channels on the postsynaptic neuron to excite or inhibit it. But without that action potential, it's unlikely that any neurotransmitter will be released. Non-spiking synapses are different in that they don't require a spike to release their transmitter. Instead, transmitter is released in a graded manner, with increased presynaptic depolarization leading to increased release of transmitter, up to a certain saturation level. Two of the most well-known examples of a non-spiking chemical synapse are the cone and rod cells in the retina. Let's begin this tutorial by creating a project and adding a new organism. Then open the behavioral editor and add two spiking neurons. Now draw a synaptic connection between them and select the nicotinic acetylcholine non-spiking chemical synapse. A non-spiking chemical synapse is modeled as a variable increase in postsynaptic conductance whose level depends upon the presynaptic membrane potential. The postsynaptic conductance has a defined equilibrium or reversal potential. This determines whether the synapse is excitatory or inhibitory. For an excitatory synapse, this reversal potential needs to be above the spike threshold, and for an inhibitory synapse, it needs to be below that value. The relationship between the presynaptic voltage and the postsynaptic conductance is determined by three parameters. The presynaptic voltage threshold is the minimum presynaptic membrane potential at which a postsynaptic conductance increase occurs. If the presynaptic voltage is below this value, there is no postsynaptic effect. The presynaptic saturation voltage is the presynaptic membrane potential at which the postsynaptic response reaches its maximum value. Further depolarization of the presynaptic neuron above this value does not increase the postsynaptic response. The maximum postsynaptic conductance amplitude is the maximum value the conductance can reach. Between the presynaptic threshold and saturation voltages, the postsynaptic conductance varies linearly between 0 and the maximum amplitude. Now let's add a stimulus to drive neuron 1. Add a tonic current stimulus and set its start time to 50 milliseconds, end time to 130 milliseconds, and amplitude to 30 nanoamps. Now we need a line chart to view the results. Create a line chart and add items to view the membrane voltages for our two neurons. Then set the end time of the chart to be 200 milliseconds. And set the collect data interval to be 0.2 milliseconds, which is the same time step used by the neural simulator. Now let's run the simulation. In this case, we did get spiking in neuron 1, and we can see that neuron 2 was depolarized. Now let's increase the current stimulus from 0 to 50 nanoamps in steps of 10 nanoamps to see what happens. At 0 nanoamps, we can see that there is a slight depolarization of neuron 2. We'll come back to this a little later. At 10 nanoamps, neuron 2 was depolarized more, even when there's no spikes in neuron 1. Now let's inject negative current into neuron 1 to hyperpolarize it. Start by injecting negative 10 nanoamps. And we get a surprise. As we mentioned before, neuron 2 seems to be slightly depolarized. Hyperpolarizing neuron 1 caused a hyperpolarization in neuron 2. This is something you would never see in a standard spiking chemical synapse. The presynaptic neuron has to be depolarized to release transmitter and affect the postsynaptic cell. But here, we hyperpolarized it and had an effect. Let's investigate a little further and halve the current to negative 5 nanoamps. This time, neuron 2 is still hyperpolarized to negative 60 millivolts. Let's really make the current small and set it to negative 1 nanoamps. This time, we see a graded hyperpolarization in neuron 2. Let's increase this a little more to negative 2 nanoamps. And again, we get even more of a hyperpolarization. So what's happening here? Neuron 1 is causing a depolarization in neuron 2 even at resting levels. This means that it's constitutively releasing a small amount of transmitter that's causing neuron 2 to become slightly depolarized. When we inhibit neuron 1, it shuts this down and reduces that depolarization. However, once we have hyperpolarized neuron 1 below a certain level, it no longer releases any transmitter and neuron 2 sits at its resting potential. This tutorial has demonstrated how to use non-spiking chemical synapses in your AnimatLab project.